March 8, 1944, somewhere over the Ruhr Valley, Germany. Lieutenant James Harker feels his B-17's No. 2 engine shudder and die. A burst of flak has torn through the cowling at 28,000 feet. Black smoke streams backward. The propeller windmills uselessly in the frigid slipstream, creating drag that pulls the bomber toward the German countryside below. His hand finds a single lever, one motion. The blades rotate parallel to the wind. The drag vanishes. His fortress stays in formation. He bombs the target and flies home. 10 men survive because of 3 aluminum blades that know how to become invisible to the wind. 8 years earlier, every aviation expert in America had declared this impossible. The story begins not with triumph, but with failure. December 1935, Boeing Field, Seattle. A gleaming silver DC-2 sits grounded beside a snowbank. Douglas Aircraft's chief test pilot, Carl Cover, stands in the freezing rain, staring at an aircraft that refuses to obey the laws of aerodynamics. The engines roar. The wooden propellers spin. The airliner lumbers down the runway and barely clears the fence. At 8,000 feet, it stops climbing. The Rocky Mountains loom another 6,000 feet higher. Passengers deplaning in Denver will have to take a train through the mountains because the most advanced airliner in America cannot reach the altitude required to clear them. Cover kicks the landing gear in frustration. Behind him, an engineer from Hamilton Standard watches in silence, running calculations in his head that will change warfare forever. Frank Caldwell never raised his voice. At 46 years old, the Tennessee-born mechanical engineer had spent 2 decades watching aviation advance through small, incremental improvements. Wooden propellers replaced by metal, 2 blades replaced by 3. But every propeller in service shared the same fundamental limitation. The blade angle was fixed. Set it for takeoff performance, and the aircraft would climb well, but cruise slowly. Set it for high-speed cruise, and the plane would barely get off the ground. It was like driving a car stuck permanently in second gear. Caldwell knew there was a better way because the mathematics told him so. In his laboratory at the Massachusetts Institute of Technology, wind tunnel tests had proven that propeller efficiency changed dramatically with blade angle. A steep pitch for takeoff, a shallow pitch for cruise. If the angle could change in flight, aircraft performance could improve by margins that seemed impossible. 40% better climb rates, 7,000 feet of additional ceiling, 15% fuel savings. The numbers didn't lie, but numbers meant nothing if the engineering couldn't deliver. The fundamental problem was hydraulic precision. To change blade angle while spinning at 2,400 revolutions per minute required oil pressure controlled to within 5 pounds per square inch. The actuating mechanism had to rotate with the propeller hub while receiving signals from a stationary governor mounted on the engine. Metal parts operating in sub-zero temperatures at altitude had to maintain tolerances measured in thousandths of an inch, while vibration tried to shake everything apart. Every aviation engineer Caldwell consulted told him the same thing. Too complex, too many failure points, too heavy for the performance gain. The Army Air Corps had officially classified his design as mechanically unsound during a review at Wright-Patterson Field in 1934, but Caldwell had credentials they couldn't ignore. As the government's chief propeller engineer from 1917 to 1928, he had pioneered metal propellers when everyone said wood was superior. He had developed the ground-adjustable propeller when fixed blades were considered adequate. His testing methodology at McCook Field had established the standards by which every propeller in America was evaluated. He had been right before, but this time felt different. Hamilton Standard Propeller Corporation had invested everything in Caldwell's vision. The company formed in 1929 from the merger of Hamilton Aero Manufacturing and Standard Steel Propeller had built the propellers that carried Charles Lindbergh across the Atlantic. Now it employed 800 workers in East Hartford, Connecticut, producing propellers for commercial and military aircraft across America. If Caldwell's constant speed design failed, the company might not survive the financial losses. The first prototype emerged from the machine shop on January 11, 1933. 3 polished aluminum blades attached to a hub that contained Caldwell's hydraulic heart. A governor connected to the engine sensed propeller RPM. When the blades needed to change angle, engine oil under pressure flowed through passages drilled into the hollow propeller shaft. A piston inside the hub moved. The blades rotated. The entire system weighed 83 pounds more than a fixed-pitch propeller of similar size. Critics said that extra weight would cancel any performance improvement. Caldwell installed it on a Stearman biplane for initial testing. Test pilot Jim Ray lifted off from Hartford's Brainerd Field on a cold February morning. He advanced the throttle. The engine roared to maximum RPM. The propeller automatically shifted to fine pitch, biting into the air like a gear shift dropping into low. The steerman leaped skyward. At 5,000 feet, Ray leveled off and pushed the throttle forward for maximum cruise speed. The propeller shifted to course pitch without Ray touching any controls. The airspeed indicator climbed 18 miles per hour faster than the same aircraft with a fixed propeller. Ray's voice crackled over the radio with barely contained excitement. This thing works exactly like Caldwell said it would. But working in test conditions and surviving an airline service were entirely different propositions. United Airlines President Pat Patterson needed proof. He offered Caldwell one chance. Install your propeller on a Boeing 247 and demonstrate that it can fly the Denver route reliably. Failure means United orders Douglas DC-2s with fixed propellers. Success means orders for 60 constant speed units at $3,400 each. Patterson's deadline was March 15th. The modified Boeing 247 lifted from Oakland on March 3, 1933, with test pilot Eddie Allen at the controls. A former Navy aviator with 8,000 hours of flight time, Allen had earned his reputation flying experimental aircraft through conditions that would ground lesser pilots. His mission was simple: fly the Denver route, clear the Rockies, and return to report. The constant speed propeller performed flawlessly. Where fixed-pitch aircraft struggled to reach 10,000 feet over the Continental Divide, the 247 climbed steadily to 20,700 feet, crossing the mountains with 5,000 feet to spare. Cruise speed increased 22 miles per hour. Fuel consumption dropped 14%. The propeller automatically adjusted to every altitude change without pilot input. Allen landed back in Oakland and delivered his assessment in characteristically blunt terms. "This is the biggest advance in aircraft performance I've seen in 10 years of test flying." Patterson signed the contract that afternoon. But success with airlines did not translate to military acceptance. At Wright Field, Army Air Corps engineers remained deeply skeptical. Colonel Oliver Eccles, chief of the engineering division, summarized the prevailing view in a confidential memo dated April 1933. Constant speed propellers introduce unnecessary mechanical complexity into combat aircraft. The hydraulic system presents multiple failure points. Weight penalties offset performance advantages. Fixed-pitch propellers have proven adequate for all current mission requirements. Recommendation: reject Hamilton Standard proposal. The memo circulated through the War Department, gathering endorsements from senior officers who trusted conventional wisdom over untested innovation. But one officer dissented. Brigadier General Henry Arnold, soon to command the entire Army Air Forces, had flown a Hamilton Standard-equipped transport and experienced the performance difference firsthand. Arnold arranged a demonstration at Bowling Field that would force the skeptics to confront reality directly. May 18, 1933. Two identical Boeing P-26A P-shooter fighters sat on the Bowling Field ramp. Same Wright R-1340 radial engine rated at 570 horsepower. Same airframe weighing 2,955 pounds empty. One mounted a standard fixed-pitch propeller. The other carried Caldwell's constant speed system. Army test pilots would fly both aircraft through identical maneuvers and report the differences. Captain Ira Eaker climbed into the fixed-pitch P-26A first. Normal takeoff roll. Standard climb rate. Ceiling limited to 27,400 feet. Maximum speed of 234 miles per hour at 7,500 feet. Adequate performance for intercepting bombers, but nothing extraordinary. Then, Eaker strapped into the constant speed-equipped fighter. The differences were immediately apparent. Takeoff roll shortened by 90 feet. Initial climb rate improved by 840 feet per minute. Service ceiling increased to 30,100 feet. Maximum speed jumped to 243 miles per hour. The same aircraft, the same engine, but radically different performance, created entirely by three spinning blades that knew how to change their angle with flight conditions. Eaker's official report demolished the skeptics' arguments with brutal precision. The constant speed propeller transforms aircraft performance across the entire flight envelope. Takeoff and climb improvements provide tactical advantages in combat situations. Increased ceiling places fighters above bomber formations. Higher cruise speeds enable pursuit of enemy aircraft. Automatic operation reduces pilot workload during critical combat phases. Recommendation: immediate adoption for all pursuit aircraft. But the most compelling argument came from an unexpected source. In October 1933, the National Aeronautic Association awarded Hamilton Standard the Collier Trophy, aviation's highest honor, specifically crediting Frank Caldwell's engineering leadership. President Franklin Roosevelt personally presented the award at a White House ceremony on December 14, 1933. The president's remarks emphasized the strategic implications. American aviation leads the world because of innovations like Mr. Caldwell's propeller. This technology ensures our aircraft will outperform any potential adversary. Roosevelt's endorsement carried weight that engineering reports could not match. Within 6 months, the Army Air Corps issued contracts for constant-speed propellers to equip the next generation of American fighters and bombers. But even as Hamilton Standard ramped up production, dark clouds gathered over Europe and Asia. In Germany, the Nazi government announced rearmament programs that violated the Versailles Treaty. In Japan, military leaders spoke openly of expansion into China and Southeast Asia. The aircraft those nations were building would soon test whether Frank Caldwell's mathematics could survive the brutal reality of aerial combat. The first combat test came not over Europe or the Pacific, but in the skies above Spain. July 1936. Republican forces fighting Francisco Franco's nationalist rebellion received a shipment of Soviet aircraft, including I-16 fighters equipped with fixed-pitch propellers. Nationalist forces countered with German Messerschmitt Bf-109s that also used fixed-pitch designs. The air war over Spain quickly exposed the limitations of conventional propeller technology. Pilots reported that their aircraft performed well at the altitude where the propeller pitch had been set, but struggled everywhere else. Fighters optimized for low-altitude interception couldn't chase bombers at 20,000 feet. Aircraft set up for high-altitude patrol couldn't dogfight at low levels. Combat demanded versatility that fixed propellers couldn't provide. Intelligence reports reaching Washington described Spanish Republican pilots abandoning their I-16 fighters at high altitude because the aircraft simply couldn't perform. German pilots in Bf-109s experienced similar frustration. The lesson was clear. Modern aerial warfare required aircraft that could fight across the entire altitude envelope, and that required propellers that could adapt to changing conditions. Back in Connecticut, Hamilton Standard faced a different kind of battle. Production. By early 1937, orders exceeded manufacturing capacity. Airlines wanted constant-speed propellers for their growing fleets. The Army Air Corps needed them for new bomber programs. Navy contracts called for carrier-based fighters equipped with the technology, and foreign air forces, watching American aircraft demonstrate superior performance, wanted to purchase propellers for their own fleets. Frank Caldwell found himself managing a manufacturing expansion that would have seemed impossible just 4 years earlier. The East Hartford facility grew from 800 to 2,400 employees. New machine shops opened in Windsor Locks, Connecticut, adding capacity for precision manufacturing. But building propellers to Caldwell's tolerances required skilled machinists who understood that a thousandth of an inch error could cause failure at altitude. Training programs couldn't produce skilled workers fast enough. The solution came from an unexpected direction. Refrigerator manufacturers Frigidaire and Nash Kelvinator, and office equipment maker Remington Rand all possessed precision manufacturing capabilities that could be adapted to propeller production. Caldwell traveled to their factories, teaching engineers how to machine aluminum blades and assemble hydraulic mechanisms to aircraft standards. By 1938, these licensees were producing propellers identical to Hamilton Standard's own manufacture, tripling total output, but quality control remained a constant concern. Caldwell established testing protocols that subjected every propeller to stresses exceeding combat conditions. Temperature cycles from 60 degrees below zero to 140 above. Vibration tests that simulated 500 hours of flight in 48 hours of bench running. Hydraulic pressure cycles that validated seal integrity under extreme conditions. Propellers that passed these trials were stamped with acceptance codes and shipped to aircraft manufacturers. Those that failed were scrapped, and the failure data analyzed to improve manufacturing processes. By mid-1938, rejection rates had dropped to less than 2%, but Caldwell remained unsatisfied. Combat would reveal flaws that no test program could anticipate. He knew that lives would depend on his propellers performing perfectly under conditions that no peacetime engineer could fully predict. September 1st, 1939. Germany invaded Poland. World War II began. Within days, Luftwaffe bombers equipped with variable pitch propellers demonstrated performance advantages over Polish fighters with fixed designs. The aerial battles over Warsaw proved what Spanish combat had suggested. Modern warfare required propellers that could adapt. In Washington, military planners confronted a sobering reality. America's air forces were woefully unprepared for modern war. The Army Air Corps operated fewer than 2,500 aircraft, many obsolete. The Navy's carrier forces were small and under-equipped. Worse, American aircraft production capacity couldn't match the industrial output of Germany or Japan. President Roosevelt called for production of 50,000 aircraft annually, a figure that seemed fantastical, given that American manufacturers had never built more than 6,000 planes in a single year. But Roosevelt understood what many military planners did not. Air power would determine victory in the coming war, and propellers were as essential as engines or airframes. Every one of those 50,000 aircraft would need constant speed propellers. That meant Hamilton Standard and its licensees had to increase production by factors that seemed mathematically impossible. Frank Caldwell, now 50 years old, found himself drafted into industrial mobilization with the same determination he had brought to engineering problems. The challenge was staggering. Current production capacity totaled approximately 500 propeller sets monthly. Roosevelt's aircraft program required 4,000 propellers per month by 1942, with continued increases as production accelerated. That meant new factories, new workers, new supply chains for aluminum, steel, and specialized hydraulic components. It meant transforming a specialized engineering company into a mass production enterprise while maintaining the quality standards that made the propellers work. Caldwell moved his family to a small apartment near the East Hartford plant so he could spend 16 hours daily solving manufacturing problems. He established 3 priorities that would guide expansion. First, simplify designs wherever possible without compromising performance. Every unnecessary part removed from the assembly meant faster production and fewer failure points. Second, develop manufacturing processes that allowed less skilled workers to produce precision components. This required special tooling, templates, and inspection gauges that made quality control nearly automatic. Third, create redundant supply chains so that material shortages couldn't halt production. By December 1941, when Pearl Harbor brought America into the war, Hamilton Standard's production capacity had reached 1,800 propeller assemblies monthly and climbing. The telegram arrived on December 8, 1941. Lieutenant Commander John Thatch, one of the Navy's most experienced fighter pilots, had engaged Japanese Zero fighters over Wake Island. His report was grim. Japanese aircraft demonstrated superior maneuverability at low speeds and could outturn American F-4F Wildcats in dogfights, but the Zeros had one critical weakness. They used fixed-pitch propellers that limited their performance at high altitudes and during rapid climbs. American pilots quickly learned to exploit this vulnerability through tactics that leveraged their constant speed propellers' advantages. Thatcher's combat memo outlined the winning strategy. When engaged by Zeros, climb rapidly to 15,000 feet or higher. The constant speed propellers maintain optimal engine RPM during the climb, while Zero pilots must manually adjust their propellers, losing precious seconds. At altitude, American fighters possess superior speed and dive performance. The Zero's lightweight construction and fixed propeller prevent effective pursuit during high-speed dives. Engage from altitude, attack and escape by diving. Never attempt low-speed turning fights where the Zero's maneuverability dominates. The Thatch Weave, a defensive formation that allowed outnumbered American pilots to survive encounters with superior Japanese numbers, depended entirely on the performance advantages that constant speed propellers provided. Fighters could climb, dive, and maneuver across the entire speed envelope, while Japanese pilots struggled with propellers optimized for low-altitude combat. By mid-1942, kill ratios in the Pacific began shifting in America's favor, not because American pilots were better trained or more aggressive, but because their propellers gave them options that Japanese pilots simply didn't possess. But the most dramatic proof of Caldwell's engineering came not in fighter combat, but in the bomber streams over Europe. The Boeing B-17 Flying Fortress represented American strategic bombing philosophy made manifest. Heavily armed, self-defending through mutual fire support, capable of reaching targets deep in German territory. But the B-17's success depended entirely on one capability: the ability to fly high enough that German fighters struggled to reach them. At 28,000 feet, where the air contained barely enough oxygen to sustain combustion, B-17s cruised beyond the effective ceiling of many German interceptors. That altitude advantage existed entirely because of constant speed propellers that automatically maintained optimal engine performance as the bombers climbed through thinner and thinner air. German bombers equipped with inferior propeller. Technology couldn't match this capability. Heinkel, He-111s and Dornier Do-17s operated at 18,000 to 22,000 feet, where British fighters could easily intercept them. The difference in operational ceiling translated directly to survival rates. 8th Air Force bombers operating at high altitude suffered 3.5% losses per mission. German bombers attacking Britain at medium altitudes suffered 7.8% losses. Over months of sustained operations, those differences became decisive. But high-altitude operations created new problems that would nearly cost Caldwell everything he had built. January 14, 1943. B-17 serial number 423124, nicknamed Memphis Belle, lost its number 2 engine to flak over Wilhelmshaven. Pilot Robert Morgan pulled the feathering lever. Nothing happened. The propeller continued windmilling, creating drag that pulled the bomber into a left turn toward the North Sea. Morgan fought the controls, trying to maintain altitude while his flight engineer frantically worked the hydraulic backup system. Finally, after 3 agonizing minutes, the propeller blades rotated parallel to the airflow. The drag disappeared. Memphis Belle limped back to England on 3 engines. Morgan filed a detailed malfunction report that went directly to Hamilton Standard's engineering department. The problem was brutally simple. At 30,000 feet in sub-zero temperatures, moisture in the hydraulic fluid had frozen solid, preventing the feathering mechanism from operating. The backup system worked, but only after the fluid warmed slightly from residual engine heat. 3 minutes was an eternity in combat. 3 minutes could mean the difference between reaching England or ditching in the freezing North Sea. Caldwell read the report in his office at 2 a.m., unable to sleep until he understood exactly what had failed. By dawn, he had identified the problem and developed a solution. New hydraulic specifications requiring antifreeze additives, redesigned feathering valves with backup mechanical systems that didn't depend on fluid pressure, enhanced testing protocols that subjected propellers to temperature extremes exceeding combat conditions. The improvements were retrofitted to existing propellers through field modification kits shipped to every Air Force base in Europe and the Pacific. By March 1943, feathering failures had virtually disappeared. Bomber crews trusted the system implicitly because it worked when they needed it most. The statistics told the story. 8th Air Force operational records documented 4,738 instances where bombers lost 1 or more engines to battle damage or mechanical failure during missions over Europe. In 4,601 cases, the feathering system worked correctly, allowing the aircraft to maintain formation and reach friendly territory. The 137 failures represented a reliability rate of 97.1% under the worst possible conditions. Comparable German bombers with inferior propeller systems showed feathering reliability below 75%. That difference in reliability translated to thousands of American airmen who survived because their propellers did exactly what Frank Caldwell's equations had predicted they would do. But the most remarkable vindication of Caldwell's impossible design came in the spring of 1944 when the Allied air forces confronted Germany's last technological gambit. The Messerschmitt Me-262 jet fighter appeared over Germany in April 1944, a revolutionary aircraft that flew 100 miles per hour faster than any propeller-driven fighter. Luftwaffe pilots flying these jets could attack bomber formations with near impunity, their speed making them almost impossible to intercept. American fighter pilots needed every advantage their aircraft could provide. P-51 Mustangs equipped with Caldwell's propellers demonstrated their worth in encounters with these jet fighters. While the Me-262 possessed superior speed in level flight, it suffered from sluggish acceleration and poor low-speed handling. American pilots learned to exploit these weaknesses. Lieutenant Colonel John Meyer, commanding the 352nd Fighter Group, described the winning tactic in his after-action report. The constant speed propeller gives the P-51 superior acceleration at all speeds below 400 miles per hour. When a jet makes its high-speed attack pass, we turn into it sharply. The automatic propeller adjusts instantly during the turn, maintaining optimal engine RPM while the Mustang's speed drops. The jet must continue its attack in a straight line because its acceleration is poor. As it passes, we reverse the turn and accelerate in pursuit. The propeller shifts automatically to climbing pitch, and we can reach 400 miles per hour in seconds. The jet pilot must dive to escape, and when he does, he's vulnerable during the dive recovery. This tactic allowed P-51 pilots to destroy 258 Me-262 jets during the final year of the war, despite being 100 miles per hour slower in level flight. The difference wasn't pilot skill or courage, it was propeller technology that allowed American aircraft to maneuver through the speed range where jets were vulnerable. By May 1945, when Germany surrendered, Hamilton Standard and its licensees had produced 530,135 constant-speed propeller assemblies. Every American fighter, bomber, and transport aircraft relied on Caldwell's engineering to achieve its combat potential. The technology that aviation experts had dismissed as impossibly complex had proven more reliable under battle conditions than the fixed-pitch propellers it replaced. Statistical analysis conducted by the Army Air Forces revealed that constant-speed propellers had prevented an estimated 16,300 aircraft losses through multiple mechanisms. Improved climb rates allowed fighters to reach altitude before being intercepted. Higher service ceilings placed bombers beyond the reach of enemy fighters. Feathering capability permitted safe return after engine failures. Better fuel efficiency reduced forced landings. The numbers validated every claim Caldwell had made in 1933. But the engineer himself never spoke publicly about his contributions. When reporters sought interviews after the war, he declined. When aviation organizations offered awards, he accepted quietly and returned to his laboratory. Frank Caldwell spent the final decade of his career developing contra-rotating propellers and turboprop systems for the jet age. He retired in 1955 at age 66, having spent 38 years advancing propeller technology from wooden blocks bolted to engine shafts to sophisticated systems that automatically adapted to flight conditions. The question that haunted aviation historians for decades afterward was simple. How had one engineer overcome an entire industry's resistance to achieve a breakthrough that changed modern warfare? The answer lay not in Caldwell's personality or connections, but in his methodology. He trusted mathematics over intuition. He built prototypes that demonstrated real-world performance. He listened to test pilots and combat aviators who understood how aircraft actually behaved under operational conditions. And most importantly, he remained stubbornly committed to the data, even when experts assured him he was wrong. In February 1974, Frank Walker Caldwell died at age 85. His obituary in the New York Times ran just 4 paragraphs, noting his Collier Trophy and his role in developing variable pitch propellers. There was no mention of the thousands of lives his engineering had saved, no acknowledgement of how his impossible propeller had helped win World War II. Just a brief notation that an aviation pioneer had passed. But in hangars across America, mechanics still serviced propellers built to Caldwell's specifications on aircraft that still flew. Warbirds restored by enthusiasts. Transport planes converted to cargo haulers. The constant speed propeller had become so universal, so completely integrated into aviation, that its revolutionary origins had been forgotten. The real story wasn't about propellers at all. It was about the stubborn conviction that mathematics could reveal truths that experience might miss. That careful engineering could overcome assumptions held by entire industries. That one person armed with data and determination could change the course of technological history. Frank Caldwell never set out to win a war. He simply wanted to make aircraft fly better. The equations told him it was possible. The aviation establishment told him it wasn't. He built the prototype anyway, tested it anyway, refined it anyway, installed it on combat aircraft anyway, and when pilots came home alive because their propellers had feathered a damaged engine, or their fighters had outclimbed enemy interceptors, Caldwell went back to his laboratory and worked on making the next version even better. That quiet persistence, that refusal to accept impossibility when the mathematics suggested possibility, that willingness to trust numbers over consensus, this was the real lesson of the impossible propeller. Not just how to build better aircraft, but how to transform entire industries through careful engineering and stubborn determination to prove the skeptics wrong. On airfields across America today, pilots still move a single lever during engine start. The propeller blades automatically seek their optimal angle. The system that Frank Caldwell designed 90 years ago still works exactly as his equations predicted. Still adapts to changing conditions without conscious thought. Still transforms engine power into thrust with efficiency that seemed impossible when he first proposed it. The impossible propeller became so commonplace that we forgot it was ever impossible at all. That's perhaps the greatest engineering achievement. Not the invention that announces itself with fanfare and recognition, but the breakthrough that becomes so fundamental, so universally adopted, that its revolutionary nature disappears into the background of accepted technology. 3 spinning blades that learn to change their angle. That was all it was. That was everything it needed to be. Every time a pilot trusts his aircraft to climb through weather, to cruise efficiently at altitude, to feather a damaged engine and fly home safely, he owes a debt to an engineer who trusted mathematics over skepticism, who built prototypes when experts said it couldn't be done, who proved that impossible was just another word for not yet achieved. Frank Caldwell's constant speed propeller didn't just make fighters 100 miles per hour faster, it made them climb higher, cruise farther, survive battle damage, and return home. It gave pilots options when their lives hung in the balance. It transformed American aircraft from adequate machines into war-winning weapons. And it did all of this through precision engineering that operated flawlessly at 28,000 feet in sub-zero temperatures, while spinning at 2,400 revolutions per minute for hours at a time. The impossible had become routine. That was the real victory. Not the engineering achievement itself, but the fact that what once seemed impossible had become so reliable, so universal, so completely proven that no one questioned it anymore. Caldwell's propellers worked. They saved lives. They won the war. That was enough. That had always been enough. The mathematics said it was possible. Frank Caldwell proved the mathematics correct. History did the rest.